Okay, I know I promised that we were going to go into the mass spring system in the earlier video, but we need a little bit of trigonometry just to make sure that we understand mathematically what's going on. So one of the things that I kept saying in the previous video is that we can take any linear combination of sine and cosine, okay, and we can show that that is either equal to a cosine or a sine. So I'm going to show this little, prove this little statement here. Let's see if we're going to show that c cosine omega t plus d sine omega t is equal to a cosine omega t minus phi, where a is square root of c square plus d square and phi is tangent inverse of d over c. Okay, so let's show a quick proof of this. So my left hand side is equal to c cosine omega t plus d sine omega t. Okay, this is a linear combination. Okay, the reason it's a linear combination is because sine and cosine have only powers of one. We only have single powers of sine and cosine here. Okay, c and d are both constants. Okay, so this is what a linear combination looks like. So now what we're going to do is we will multiply and divide both sides by square root of c square plus d square. Not both sides, only the right hand side. So I'll multiply by square root of c square plus d square, and then what I'm going to do is I'm going to divide each of the terms by square root of c square plus d square. So this gives me this plus d divided by square root of c square plus d square times sine of omega t. Okay, as long as c and d are not both 0 at the same time, all this works well. Okay, now that we have this, what we recognize is this. If you look at this, the c over c square plus d square, square root of c square plus d square. Okay, what we know is that the first term here, this, has to be less than 1. Okay, we know that square root of c square plus d square will always be greater than c. Okay, or at the most, equal to c. So we know that it is less than or equal to 1, and this, in a similar manner, we know that d divided by square root of c square plus d square is also less than or equal to 1. Okay. So the good thing is when things are less than or equal to 1, and it will be at the greater than minus 1. Okay, we don't really care about that right now. But when we know that this is less than or equal to 1, then we can basically say replace them with either a sine or a cosine value, because we know that sines and cosines are always going to be less than 1. So in order to achieve this, what we're going to do is we're going to draw a right angle triangle. Okay, we're going to call the angle phi. We're going to call the opposite side D. We're going to call the adjacent side C. Okay, and so the hypotenuse now could be c square plus d square. Now you see in this triangle, we know that cosine of phi is equal to c over square root of c square plus d square. Okay, the sine of phi is equal to d over square root of c square plus d square. And what we also know is that tangent of phi is equal to d over c, which implies that phi is equal to tangent inverse of d over c. Okay, so this is one part of the proof statement here where we had to show that phi was equal to all that. So we got that part there. Okay, now that we have all this, let us replace our left hand side once again with square root of c square plus d square times cosine of phi cosine omega t plus sine of phi sine of omega t. Okay, now the square root of c square plus d square, I'm going to just say that let that be equal to a, and then inside the parentheses I'm just going to switch the order. Okay, and we can do this because the cosine function is symmetric. So this, okay, and so what we end up getting is from the identity for the expansion of cosine of a minus b, we see that this is equal to cosine of omega t minus of phi. So what we've shown is that c cosine of omega t plus d sine of omega t is equal to a cosine omega t minus phi. Now, on the other hand, if we chose our phi to be something else, okay, and we ended up calling the opposite side c and the adjacent side d, okay, then we would replace it with, it'll be sine phi for c over square root of c square plus d square and cosine phi for the other one, and you would end up getting a sine function. So it really doesn't make any difference. Okay, a cosine and a sine function are pretty much identical. They're just shifted by a certain amount. Okay, so what we get is we get a cosine omega t minus phi is equal to all this. So we've shown an important thing, and that's why I can write my, in general, I can write my cosine of my sine function as, you know, a cosine omega t minus phi, plus or minus phi. Okay, so that's one relationship that we needed. Okay, so this is proved now. Another thing that we would need also, well, we will use, is that this identity, that we know that sine squared of theta, any theta, plus cosine squared of any theta is equal to 1. We're going to use this. Okay, so keep this in mind, and I hope you all know how to prove this. The proof is very simple. If you take an angle theta, let's just call this side A, B, and let the hypotenuse be C, then what we know is that sine of theta is equal to A over C. We know cosine of theta is equal to B over C, and we also know that C from Pythagoras theorem is equal to square root of A square plus B square. Okay, so this implies that sine squared theta plus cosine squared theta can be written as A square over C square plus B square over C square, which is A square plus B square over C square. But what is C square? C square is A square plus B square as well, and so this is equal to 1. Okay, so keep this in mind. These two, you know, relations are going to be useful, and you know, we're going to, when we write down our when we try to figure out what our functions are going to be like, we're going to use these ideas. Okay, so that is that.